Hello, this will be a demonstration of proposition 31 of book 7 of Euclid's Elements, which says that any composite number is measured by a prime number. This is one of the most important propositions in not just all of Euclid's number theory, but in the entire Elements. All we're given is some composite number A. What we want to prove about this composite number A is that there is some prime number which measures it. Because the number A is composite, then just by the definition of composite numbers, which is definition 7.13, some number's going to measure it. We're going to call that the number B. So the number B measures the number A. Now, if the number B is prime, then we've done that which we set out to do. We set out to prove that some prime number measures A. If B measures A and is prime, we're done with the proposition. But if the number B is instead composite, for the same reason that because A is composite, some number will measure it. If B is composite, some number will also measure it. We're going to call that the number C. So C measures B. Now because C measures B and B measures A, we can just say by a property of numbers that C also measures A, right? So 9 measures 18, 3 measures 9, so 3 measures 18. Just very obvious. So the number C measures our original composite number A. Now if the number C is prime, then again, we've done that which we set out to do. We set out to prove that the number A is measured by some prime number. If C is prime and it measures A, we're done. But if the number C is composite, then we can go through this same set of reasoning and say that, okay, if the number C is composite, then some other number D will measure it, and that number D will also measure A. We can do this for any length, right? We can always find, if our measuring number is composite, we can find some other number which measures it, just by definition of being composite. But this cannot go on infinitely. We will eventually have to hit some prime number. If we don't hit some prime number, then what's going to happen is that the number A, our composite number A, will be measured by an infinite number of other numbers, each of which is less than the one before it. But this is impossible with numbers. There's not an infinitely small number. You're eventually going to hit something, and that something will have to be a prime number because number is not infinitely divisible. You're going to have to hit something that you can't divide up any further, something that isn't measured by another number besides, of course, the unit and itself. And this is the definition of a prime number. So we're eventually going to have to hit some number which measures A, which is itself only measured by the unit and itself. And this is the definition of a prime number. So we find that some prime number will eventually have to measure A. And this is precisely what we set out to prove, which means we are done with the proposition, therefore, etc., Q, E, D. Now, there is another way you can go about proving this. You can say that, okay, A is composite. We're going to find the least number which measures A. We're going to call that B. Now, B is either prime or composite. If it's prime, we're good to go. If it's composite, then we're going to find the least number which measures it. And by the same reasoning, if C measures B, B measures A, C measures A. But then we find that C also has to be the least number which measures A. But this is contrary to how we constructed B as the least number which measures A. So we end up with a contradiction and just an impossibility if the number B, if the least measure of A is not prime. If it's composite, we end up with this absurdity. So the number A is measured by some prime number. That's another way you can get at the same truth. Let's just do an example of this real fast. So we're going to take our number 108. This is a very nice number. Now, what numbers measure 108? Well, the number 6. The number 6 measures 108. And if we divide 108 by 6, we get 18. Now, 18, well, that is measured by 9. So you can divide that by 9, and we get 2. 2 is prime. We can't go any further with this. So we see that this proposition holds. Now, this is not a proposition, just induction, where we've tried enough numbers and we've never found one that is not measured by a prime number, therefore all composite measures are measured by a prime number. This is not that sort of argument. That would be like the black swan fallacy, right? We've never observed a swan that is black, therefore no swan is black. But this is not the sort of proof we're dealing with, that just because we've never found a number that is not measured by a prime number, we're then concluding that all composite numbers are measured by a prime number. That is not what we're doing in this proposition. Instead, what we're showing is that if there is no prime number which measures A, then we end up with this impossibility, an infinite number of numbers which measure A, each of which is less than the one before it, which is, again, impossible. So if the contrary is impossible, then we have to assume that our original proposition was true. So because it is impossible that there is no prime number that measures A, we have to then conclude that there is some prime number which measures A, and that is more or less the shape of the proposition. That's all I've got to say about this one. I hope this was a good explanation of it. This is not only one of the most important propositions in the elements, it's also one of the most confusing ones. There's not really another proposition like it, so it can be difficult to understand. I hope I've explained it in good enough detail. If it hasn't, of course, ask me in the comments. I'll respond. But with that out of the way, I'll end the video here and move on to proposition 732.